Let's do some examples. Okay, so this stuff is abbreviation for cyclopropane, and it is not a circle. It is a triangle of carbon atoms, each bonded to two other carbon atoms and two hydrogen atoms. Now, this is not a particularly happy camper. The bonds are not bond angles that carbon likes, so it decomposes into stuff. And what we're going to figure out is if we have a flask with 0.25 molar cyclopropane, what's its concentration going to be after 8 minutes? So this is the perfect application of the exponential version of this integrated rate law, that the cyclopropane concentration at our later time is equal to the initial concentration times this e to the negative kt. And for this, to finish this, you need to be aware of the fact that the rate constant for this decomposition is 6.7 times 10 to the negative 4 per second at 500 degrees Celsius. And from here on in, it is pretty much plug and chug. One thing that you do want to make sure is that these the arguments of a natural log or of an exponentiation operation should technically be unitless. So it's important that the rate constant and the time component have the same unit in this case, and there's a possible mismatch because I gave you the time in minutes, and this rate constant has units of inverse seconds. So I chose to convert the 8.8 minutes into seconds, and this is hopefully something I hope you can do at this point, and that's 528 seconds. And now it is pretty much plug and chug. So the concentration at time t is equal to the initial concentration, 0.25 molar, times e to the negative 6.7 times negative 4, and here inverse seconds, times 528 seconds. So if you look at this operation here, you've got inverse seconds times seconds, which cancel out, so this is unitless. I would recommend, now make sure you practice this because different calculators handle this E argument a little bit differently. So make sure that you follow along and get the answer that I do. For most calculators, it's going to be something on the order of multiply these two numbers, make it the negative. Remember, you do not do that with a subtraction sign. You do it with the change sign key. Raise it to E and then multiply it by 0.25. And if you do it correctly, you should get an answer of 0.18 molar. Now, does this answer make sense? It's reasonable, and it's reasonable because it is a lower number than the initial concentration. If after some time your concentration has increased, something has gone wrong. If that thing is a reactant, so the concentration of reactants go down, so we would want a smaller number. It should also be a positive number. The lowest concentration possible is 0. A negative concentration is nonsensical. So this is, a more straightforward version of this question. Now, this is the same concept, but the math is a little bit difficult, or a little more involved, we'll say. So try this one out here. We're going to figure out how much time it takes to go from 0.25 molar to 0.15 molar. Again, with the same initial, setup here, that the rate constant at 500 degrees Celsius. The only difference here is that now in this case we're solving for the time and not one of the concentrations. So I would recommend here just plug in what you know and then rearrange things to solve for what you don't know. So I know the concentration at time t, I know the initial concentration, I just don't know what the time t is. So this is our target concentration, this is the initial concentration. we can get those. So the idea is that you probably want to isolate that E term by itself. And the way that you get rid of that E term is to take the natural log. So the natural log and E of those are opposite operations. But first, I think I took that ratio, so 0.15 over 0.25 is 0.6. And now, so the natural log of 0.6 is equal to KT. So just to be clear, because I didn't explicitly put this in this slide, in case you're not used to it, I'll do this off to the side here. The natural log of anything, so natural log of e to the something is just the thing. So that's how we got to there. Pointer back. And from here on in, it is just algebra, so we can solve for the time is equal to the negative of natural log of 0.6 divided by 6.7 times 10 to the negative 4 per second. Now, what are the units? We have 1 over inverse seconds, so this will give us seconds, which is good. And that gives us 762 seconds. Be careful with this negative sign. Again, so this should be a positive result, right? We're going from a high concentration to a lower one, so that should be a forward elapse, forward time. This happens a lot because this natural log is a negative quantity, and people forget either the negative that comes out of here or this negative sign, which was this one right here. And if you miss one of them, you get a negative number, which should be a sign that something has gone wrong, because it should be a positive number. And does it make sense? Compared to the example that we just did. There we went from 0.25 to 0.18 molar in less time. So if we're going from 0.25 to 0.15 molar, you would expect a time that was greater than what we just did in the last slide, which it is. So this answer looks good. So these are just, this is another example. There's actually 2 questions in here that are useful. I'm not going to elaborate on them. I've just, here's the question. Here is the write-up for them, or the complete solution for them. Again, make sure you can do these. This is a good check to make sure that you are doing the natural logs and the exponentiation operations on the calculator correctly, and make sure that you can get, these answers. Next thing we're going to talk about is half-lives. So what is a half-life? A half-life is something that is often used to describe a reaction, or how fast or how slow it is. It is often denoted with the symbol T sub 1/2, and it represents the time it takes to reduce by a factor of 2, or by 1/2. And so if the half-life is small, very short, that's indicative of a fast reaction, because it doesn't take long for this stuff to reduce. Now let's think about this. So let's hypothetically, let's go from 1 molar to a half molar. So that would be, we'll call that half-life number 1. And then you could go from 0.5 molar to 0.25 molar, units here, and that would be half-life number 2. And finally, let's do one more. So we could go from 0.25 molar to half of that, which is 0.125 molar. Now what I want you to think about is how would these times compare half-life number 1 and number 2 and number 3? Because remember that for first order reactions, rate is equal to K and then times, the concentration to the first power. So the rate is continually changing, right? Because it depends on the concentration, and more importantly, it's continually changing, but in one direction, it's continually getting slower. Because as the concentration drops, the rate's going to drop. So would you expect these half-lives to take more time? Would it take more time to go from 0.5 to 2.5 than it would from 1 to 0.5? So, as is often very illuminating, let's just do the math. I'll switch to black here. So this is a pretty straightforward setup, and I'm just going to say that, so we know that, and I'm going to use the exponential version of this. So the concentration of A at any particular point in time is equal to the original concentration, A sub 0, times e to the negative kt. So all I'm going to do here is substitute in for my A of t. Now I'm just going to say that's going to be equal to the initial concentration divided by 2. So this equation now becomes try this again here, sorry about that. A0 over 2 equals A0 e to the minus kt. And what you see here is that you've got an A0 on each side, so you can just cancel that out. So that gives us 1/2 equals e to the negative kt, where k is the rate constant. And to get rid of the exponent, take the natural log. So here we've got the natural log of 1/2 is equal to negative kt. Now at this point, it's important to note that the natural log of a number is just another number, which in this case I happen to know is 0.693, negative 0.693. And that equals to negative kt. And now I can here just solve for the t, so now I'm going to start to call this the half-life. T1/2 is equal to 0.693 over k. And why is this an important result? Well, it's a constant. So what that means is that this half-life, and this half-life take exactly the same time. This is actually one of the distinguishing features of first-order kinetics, is that is the case. How does that work? Well, yes, the rate is continually slowing. But there is also, for each successive half-life, less of A to react. So the reaction is slower, but there's less stuff to work on, and these two factors happen to exactly cancel. Making the half-lives, again, exactly the same time. Now, the fact that I pointed out that this is a quirk of first-order reactions implies that that's not the case for the other types, and we will see that in a later slide.